Hi. So in the last video we saw how the dist plot is very important in case of numerical features and how we can quickly eliminate few of the features by just looking at the distribution of them. So by just looking at the distribution of them we can eliminate few of the features. A similar kind of technique which we will be applying now is known as the distribution analysis now. So which kind of whether the particular column is following a Gaussian distribution, a left skewed distribution, or a right skewed distribution, like that. So for that I'm going to use the SciPy library, that is from scipy.stats, import stats, and then I'm going to define this function which is draw plots, which takes in the parameters as data frame and column. So let me just import this library, and then draw plots will take up this data frame and column function. So first I'm gonna make my figure, that is plt.figure as this, and then I'm gonna make subplot 1, 3, 1. What this means is 1 is basically the row and 3 is basically the columns. So 1 row 3 columns, and from that 1 row 3 column I'm selecting the first column for plotting the histogram. As you can see here, this is 1 row, and in 1 row this is column number 1, column number 2, and column number 3. So I want to plot column in column number 1 I want to plot histogram, so that is why I kept column number 1 over here. Okay, so plt.hist, in matplotlib there is the hist function which is used to plot the histogram. So I'm just passing df of call. So this df of call is nothing but a series object which will get passed, and then I want that color of the histogram to be magenta. So this plot will be plotted at the first column. Now in the second column plt.subplot 1, 3, 2. So this basically indicates that first row has 3 columns, and of that 3 columns I'm selecting the second column now. So this is the second column. So in the second column I want to plot the probability plot. Now what is this prob plot is basically this prob plot is nothing but it's a kind of a it shows a kind of a Gaussian relationship between variables. So what do I mean by that? Let me just explain it quickly. Okay, so what do I mean by that is basically yes, so in Gaussian for let's say that over here we are having a Gaussian distribution curve like this. Okay, we are having a Gaussian distribution curve, and we want to plot a dist plot of we want to plot a pk probability plot of it. So what happens is simultaneously I'll take this point over here. This ranges from like minus z to z, if I'm not wrong, minus sigma to sigma basically, and then here it is 0. So based on the formula that z is equals to x minus z score is equals to x minus mean, that is x minus mu by sigma, where sigma is the standard deviation. Based on this z score, basically we will plot the distribution over here. So for example, this point is there, this point we will plug it into this, and then we'll get a point over here. Okay, this point is there, this point we will plug it into this formula and we'll plot it over here. So basically over here we will be having a red line like this, which says that this will pass from origin, that is 0. So in standard normal distribution we know that the mean of the thing is 0 only, right? As you can see from here also, it will just pass from this. This basically means the standard normal distribution starts from -3 to 3 over here. So that basically says that what that basically indicates is yeah, this is -3 to 3. That basically indicates that this is a standard normal distribution where mean is 0. So whenever mean is 0, so this formula basically becomes x by standard deviation. Okay, x by standard deviation. So simply you just plug in this values over here. These values are over here, these values are over here. Just plug these values into this formula and plot them over here. Okay, so for example, if I plot them over here like this, let me just erase and redraw and show it to you once again. So let me say that. Okay, so let me say one thing. Yeah, so over here, for example, the scale goes from -3 to 3, right? So -3, -2, -1, 0, 1, and 2 and 3, right? So over here, suppose that this point is there over here, this point, I'm finding this value, I'm plugging that value over here, I got a result over here, somewhere over here I got a result. So this is nothing but my y value, and this is nothing but my x value. Okay, So now this point I calculated the y and x value, I plug it into this, I got the result over here somewhere. Now similarly I will be doing for every data point which is a part of that centralized distribution, and I observe that I'm getting some kind of data points in this fashion over here. This is kind of scattered. So now this kind of thing I'm getting. Okay, so if I draw a particular line over here like this, so I see that this kind of distribution is not centrally distributed, because it's kind of varying around the mean. So basically, if it's exactly a centralized distribution, what will happen is you will be getting the blue dots on the line only. So whenever you get blue dots on the line, or little bit they are around the variation of it, that means they are perfectly centralized. So as you can see, for example, this one like this, exactly this. So you can see that this distribution is a perfect bell curve, and based on this perfect distribution only, this line is getting plot. So this is the probability plot, which is also very important in order to understand how the distribution of the data is, whether there are few outliers or not. We can see that there is one outlier which is over here, and it's visible over here also. Okay, so this is all about this prob plot. And then box plot, we use box plot for finding out whether there are outliers or not. So in box plot, basically it will help us to know whether there are outliers in our distribution or not. So these are the three combinations of plots which I'm using in the subplot. So and plt.show will plot all these three columns. So this is all about this draw plots function, and I'm gonna find the list of so for every column I'll just plot this. So distribution plot for feature calls of I, that is nothing but first feature is density. So distribution plot of density is, so density will be passed over here, df and density will be passed over here, and all the three plots will be plot for the column named density. So we can see the distribution, we can see the histogram for this like this. Simultaneously we for all plots we can see the functioning. So for all plots we can see the functioning, and we can see that every value is almost like every function or every feature is a Gaussian distributed, either a left skewed, right skewed, or centrally skewed. So this is this is like a bonus thing to us, because we rarely get Gaussian distributed things. So once we are getting our normally distributed values, now there is no need of any kind of pre-processing only, because it's almost done. If everything is under normal distribution, there will definitely be good results out of it. So there is no kind of more kind of extraction and everything which is required from this. But what we need to do is we need to eliminate few of the features. So eliminating few of the features is a technique of feature selection. So we'll be looking at feature selection in the next video. Before that, we will be also looking at the outliers, if there are any outliers. So over here we can see that I kept an upper limit and lower limit. So this is a standard normal distribution formula, where we like this -3 is there. No, if we are having values less than -3, that means that is an outlier for us. If we are having values greater than 3, that means that is an outlier for us. So basically what this entire thing is saying is this. Okay, just a second, I'll just erase it. Yeah, over here if I just look at the formula over here, what this is saying is yes, so this kind of formula is being used here. So yes, so basically upper limit dot append df of I dot mean plus df of I dot std times 4. So as I said that in Gaussian distribution we have the limits like from -3, -2, -1, and this is 0. Here we have 1, 2 and 3, and the bell curve will be like this, and this is a perfect Gaussian. Okay, so if I'm having values less than -3, that means it's an outlier for the centrally distributed curve. If I'm having values greater than 3, that means that is the outlier for this curve. So that is what is written over here. So lower limit must be lower limit must be within the range from -3 to 0, and upper limit must be within the range from 0 to 3. If it is beyond -3 and if it is above 3, that means that is considered to be as an outlier for this normal distribution. That is what this entire 2 lines of code is saying. Okay, so I'm calculating that, and then that is what it is written here. df calls of upper limit if there are values which are greater than the upper limit, and if there are values which are less than the lower limit. That means if there are values which are less than the upper limit, that is 3, if there are values which are greater than the upper limit, that is 3, and if there are values which are less than the lower limit, that is -3, if there are so kind of values, just ignore them. So that is nothing but our outliers. Okay, so if we just see, we do not get any kind of outliers here, so it's automatically handled. As I already said that if the distribution is completely or purely Gaussian, there is no chance of getting outliers. Even these 2 outliers are automatically skipped when we do model processing and everything. So there's nothing to worry about outliers. We get outliers when there is some kind of skewness in the distribution. So that's not an issue to be worried in this case. So that's all for outliers. We'll be looking at feature selection in the next video.